So therefore, today we're going to, if you remember last time, we took us through the processes that usually involve in writing machine learning based research papers. And then we are going to continue also from where we stop. So which is going to be the result of investigating the feature selection. If I'm not mistaken, this was where we stopped the other time. Yeah, so if we remember, we took us through at the beginning. We start, it's been a long time, we'll be starting. So developing research paper was in the format. We discussed how to write the abstract, which we can all see in the writing research papers, video 1, 2, and 3. So today is the 4th edition on how we document the research outcome. So we discussed the introduction, we differentiated we stated the differences between abstract and introduction and how to make them the way they should be. We move on to talk about review of related literatures, which are very important before you can really even establish the importance of the problem you are trying to address. Because if there's no need from it, from the literature point of view, it will definitely not make any meaning to go out with such a system. Then we also try to look into the description of the proposed techniques. So where we usually recommend that at least 2 machine learning techniques are often involved when we dealing with a system like this. At least it's recommended to have at least 2 machine learning techniques. If there's more, that's better. And then we also mention the need for us to describe the techniques from technical point of view, technically. So which is more mathematical, because most machine learning algorithms have mathematical backgrounds. So, and then where we recommended the presence of the need for mathematicians to really come in and do professional job in the proper representation of those techniques. Then we move to the empirical studies, which is actually what machine learning is all about. Try to get data, play with data, and hopefully get the best out of the data we have. So we describe the empirical study, description of data sets, the statistical analysis, finding out the correlation between each attribute and the target. We have the experimental setup. We have the experimental setup, and then we move on to have the experimental setup, where we describe and recommended that it's better for us if we can have a kind of a flowchart that would describe the procedures we are taking in doing the work, which is we presented a generic procedure wherein you have the data gathering, we have data preprocessing, we are applicable, we have the model building, where we check the model if it is okay. There might be the need for us to refine the model, where you try to do parameter tuning. You try to play with your parameters. This is very important. Got a couple of questions related to this, and like I said, we are going to describe parameter optimization as a topic after some of these sessions. So we are going to describe some of the options that are available to us when we are dealing with optimization of our parameters. So parameter optimization is very, very important. Parameter optimization can move a model performance from as low as 50% to 90%, depending on the problem you are solving. So that is why it's very important that we also understand and know how to carry out the parameter optimization in an appropriate manner. Once you are done with parameter optimization and it's okay to your own liking, then you build the final model, validate the model, do prediction, and then analyze your results. We see that it's always good to describe our experimental setup in kind of, as you know, that figure do represent things in more better and clearer way. So this is another representation depending on the problem you are solving. seeing the data collection, hyperparameter optimization, so machine learning simulation, predicted labels. You check if the performance is satisfactory. If yes, go ahead. Otherwise, you have to go back and do the parameter optimization. So parameter optimization is very, very important. It goes a long way to determine often the performance of your models. And then we move to the performance measure that you need to also tell your reader how you want them to judge the outcome of your experiments. So what is going to be the basis for judging them? We describe different performance measure from if you are solving classification problem, if you are solving regression problem, we have different performance measure for them. And I said, it is good for you to check the literature in your area and try to use those performance measure that have been used in the literature, because that's the basis for comparing your work with earlier work. If those people in literature use a particular performance measure, it is also expected that you use the same performance measure. You can only add more if you wish, but you can't use less than what they are used to in that particular field. And I also mentioned that often fields, different fields have their different performance measure, as this case may be. And as I was saying, so when we look at the performance measure, I also mentioned that each field have unique performance measure that are used in the area, and depending on the problem that we are solving. We're talking of classification problem, we'll be talking of making use of accuracy, F measure, area under the curve, and especially confusion matrix. And we're talking of regression, we'll be talking of root mean square error, root mean square error, correlation coefficient, and of course, trying to also plot the predicted value against the actual value that were given. So when we look at that's the performance measure. So we try to use the appropriate performance measure. Then we move to the optimization strategy, where we also describe for ourselves how we optimize the parameters. So this, inshallah, we're going to come back later. We have detailed discussion or topics on how to do parameter optimization, the different methods that are available, and then how to ensure that we are working with the best possible parameters. As we always say, that in the principle in machine learning is let the data speak. So if we say, if the principle is let the data speak, which is the principle that is established in this field, then how are we going to make the data speak very well, if not for the parameter that we need to make sure that we are working with the best possible parameters. Now, so we also mentioned that in the parameter, you can make plots of parameters to see how the accuracy is changing with it. Like this cost function, when it was 1, you can see the performance. When it became 5, at a point in time, the accuracy goes up. It means that this data set we are modeling is better suited for when C is set to 25. So we can conclude that, okay, the best parameter for these, the best parameter value for this, our C is going to be 25, for example. So, and then we also differentiated between the hyperparameter and the parameter. So hyperparameter are those parameters that directly affect the models themselves. So we discussed it, and then we went into the research and discussion. We described several ways that we can enhance the discussion of results. We made it clear that discussion of results doesn't mean that we just lift. We should not just lift what is already, what has been reported in the table, and then we decide to reproduce it in Word. According to the table X1 above, we can see that techniques 1 is better than techniques 2. As it's achieved 90%. We can see that from the table directly. We don't need to do that kind of repetition, but rather we bring more informative discussion up. What is the percentage improvement that one technique offered over the other techniques? These are stuff that we need to work on, rather than just lifting what is already in the table and then reproducing it again. So that will be like just repetition. So we described this also last time. So, and finally, we stop at the point that we also say that, okay, once you finish with the initial experiments, these are all, you use all the features that were given to you, describe the result. Did you get better result than those who work published earlier, or than those people that work in the same area? If yet, well, that could be room for celebration because you already achieved better result that you are looking for. Uh, then the next phase of your research can be, okay, how can I enhance what I have gotten now? And one of the ways of trying to enhance result is to try to see how can I reduce the number of features that I'm going to use in my modeling. For example, you have data set that is having like 25 features. When you have data set with 25 features, in that case, so you are going to see, can I reduce the number of features to like 4, like 5, to make things to be faster, because when you reduce the number of features, the model is going to be faster for the computational, from the computational complexity point of view. And also, imagine you are building a machine learning solution for medical prediction, let's say diabetes prediction. So, and then you need to have like 25, maybe you need to, already the data came from the medical college with 25 features. So, and out of these 25 features, 23 of them are going to be medical tests that people need to go to medical center to do tests. So if people need to do 23 medical tests before they can use your model, you can see that it's going to be a lot of challenges. See, from financial point of view, financially, how are you going to ask everybody to go and do 23 medical tests? Again, also from the risk that is involved. Imagine somebody on the sick bed, you need to extract blood for 23 medical tests. That is too much. And so many other risks that are associated with it. So that's why, even though after using all these features, we were able to get like 95% accuracy, because the earlier guy got like maybe 85. So that's a very big improvement we have provided. But then we don't stop here. Of course, you can go ahead, you can end the research at this point in time. As we know, research is always a continuous process. You can end your research and then document what you have gotten. At least you have achieved improved accuracy. So even at that point, you are now thinking, okay, in future, maybe in future I might think of saying, how can I improve it further? Maybe then I'm going to talk about maybe ensemble. And then told us last week, like the other time, that instead of thinking of ensemble immediately, one thing we can think of is what we call feature selection. Feature selection. So ensemble is higher level. As you know, once you go into ensemble, you try to get better result. But before you go to ensemble, try to do feature selection, because often you get better result when you can do reduction of features in a systematic way, not just at random. Anyway, so that was why last time we said that, okay, next time we're going to look at, after you have done the experiment for the whole data, now can we try to see, can we investigate the effect of feature selection? Even though you have achieved something you think that is better for you, it's okay. 95% improve, 95% accuracy compared to 85 earlier. That's a very big improvement. But however, can I improve it further? That's why I call it, usually it's an optional, usually optional here. So usually I call it optional. That is a result, investigating the effect of feature selection is not compulsory for you. It depends on what you want to achieve. So sometimes maybe after the experiment, the earlier person already achieved like 93, and you struggle to get 93. So you now try to see that, can I even take it further to get the better result? Sometimes, so maybe you have gotten 93%, and the earlier guy that worked in the area also got 93. So you still want to get something better. So at that point in time, it becomes very important for you to look for, how can I get something better? So one option is for you to investigate the effect of feature selection. It's a very simple way of doing that I'm going to introduce also, even though there are several methods of feature selection. In one of our earlier videos, we describe feature selection as a topic. And hopefully also we have opportunity of coming back to revise them and introduce also some of the latest updates in those areas. Now what is feature selection? So let's say we are having 25 features. So we want to reduce the features to like minimum. We don't know, maybe we're going to get best 5 or best 7, who knows? So that, and then there's something we call cost of dimensionality. Usually the more the number of features, the more the number of samples that you need to get reasonable results. For example, if you gave me data set with 25 features and you only gave me like 300 samples, without even more ado, I know there's going to be a big challenge in this kind of data, because 300 samples for 25 data feature is just too small. In an ideal situation, like we mentioned earlier, under the topic of cost of dimensionality, I said if you have like a 10, if you have one feature, you are given one feature. I said the estimated number of samples or cases that you need to be able to get reasonable result is 10. When you have 2 features, you need like 10 raised to power 2. When you have 3 features, you need 10 raised to power 3. So when you give me like 25 features, I should be looking up to have 10 raised to power 25 samples. But now you gave me only 300. So I still go into modeling and see what I can get. But for sure, the number is lower. So we need to think of one way is to get more data. But usually your client will tell you, we are sorry, we don't have any data. This is the only data we have. In that case, you cannot manufacture data set. So you have to go back to your own machine learning techniques and see what can I do to improve my accuracy. So one way to quickly look at before you even start thinking of ensemble techniques is to quickly check, can I reduce the number of features? If you can reduce this feature to like 5, maybe it's matching up to a little bit of 300. At least it's better than 25 to 300 because the expectation here is too much. We were expecting 25 raised to power, sorry, we were expecting 10 raised to power 25 number of samples, and someone gave us 300. So if I can reduce 25 to 5, that means with 5, I should be expecting like 10 raised to power 5. I'm getting 300. At least it's better. Though we are not there yet, but at least it's better. It's closer. Expecting 10 raised to power 5 and you got 300, compared to someone that is expecting 10 raised to power 25 and getting 300. We can see that the differences are very much kind of unique. So in that case, we try to see how can we do feature selection to reduce the number of features. Now, in doing this, I introduced us to a very simple one I call correlation-based feature selection. Correlation-based feature selection. You try to check the correlation of each of the attributes that you have been provided with in relation to the target. So, and the good thing about the feature selection, the correlation-based feature selection is very simple. Very, very simple. So it's not going to add to your computational complexity. You can do your correlation in Excel file without even using the computational environment you are using for your modeling. So for example, I have X1, this is feature 1, which is the weight of the patient. For example, we have feature 2, which is maybe the blood glucose level, like that. So I want to get what is X1 and the output. Output is Y, diabetes or not. X2 and the output. So I want to find this one is going to be 0.96. Why this one is 0.8, and then we have others. So we arrange them according to the size. The one that are higher value means they are more correlated. It means they have more information that can assist our machine learning to get better result. So we go for that. So in this case, let's say we have like 25 features, example we are doing. So we arrange them in descending order, starting from the biggest, and then we keep going down. Note that you might get some minus, negative correlation. So when you get negative correlation, for example, I have minus 0.08, and then I have another one that is 0.75. When I'm going to arrange it, minus 0.8 will come before is 0.75. Because in correlation, it could be negative correlation, it could be positive correlation. That is fine. So when you're arranging them, you have to find the absolute value in the arrangement. But take note that this is negative correlation. Because negative correlation only means that while one is increasing, the other one is decreasing. While positive correlation means the two of them are increasing or decreasing in the same direction. So therefore, once you arrange them, then you try to follow this simple recursive based feature elimination. It's very simple. So we can use the tenfold crop validation to do it, or we can use our holdout partitioning. Now, this is the description of the simple algorithm to do your feature selection. What do you do here? One, you first build the classifier. Maybe it is SVM, anyone you are using, or KNN, my favorite. It's very simple. So maybe you build KNN using all the features, V features. Now you calculate the correlation of all features to the targets, then arrange them in descending order, like I've mentioned before. And then choose the best V divided by 2 features. So if I have like 25 features, I arrange them. So in the first time I'm going to select, 25 divided by 2, which is going to be 12.5, which is approximately 13. So select the best 13 attributes. That is, attribute that had the highest number of the highest correlation as arranged here. So, and we also have it in this table. I'm going to show us again briefly. We have this information here already in the table. You can see it here. You can refer back to previous video. This is correlation. So arrange them in descending order. So 0.97 will come first, followed by 0.963, followed by 0.96, and then followed by negative 0.8109. So you're going to count them like that. Then you select the best one to start with. So now you select the best half of it, which we've calculated to be 13. So I'm going to use, so we use all the features. We put the result here. You have your result already here. Maybe you got 0.93, techniques 1, techniques 2, you record the result. Using V divided by 2. So the first one now is 13. So I will run the experiment, get the result in here and see what you get. Now repeat until one feature is left. So it means I'm going to go back here always. You know, I've selected 13. From those 13, I record the result. Now I will divide the 13 by 2 again, divided by 2. That's going to be 6.5, which is approximately 7. Select the best 7 features from the top. Run the experiment. This is for 7. Then do that again, divide by 2. That's going to be 3.5, which is approximately 4. So select the best 4. Best 4. Then the next divided by 2, select the best 2. And then finally select the best one. You keep repeating that. We call it recursive feature elimination. You keep repeating it. So we call it recursive feature elimination procedure based on correlation coefficient. It's very simple, and then it reduces the number of features faster. Because if you have very few features, as I'm going to mention later, you can do the exhaustive method, which is if I have only 3 features, X1, X2, X3, X4, and X5, for example. In that case, I might not need this. Let's just say 3. So what I need to do is try feature 1 only, see what you can get. Try feature 2 only. Try feature 3 only. Then combine X1 and X2. Then combine X1 and X3. Combine X2 and X3. Then combine X2 and X3. So you do different combination, and finally you combine X1, X2, X3, and see which of this combination works for you. You can easily do that if you have very few features. However, when you have huge number of features, like 25, then you can imagine the combination, because this is combination problem now. Imagine having to combine X1, X2, X3, X1, X2, X4. You know how many times you're going to try. Sometimes it goes into computational. Computationally, it's not usually advisable. So this is why we have other methods that have been advised, like this recursive feature. So in the recursive feature, at every level, you are dividing it by 2. So you are reducing it by half, until you get to, you are left with only 1. And when you are left with only 1, you run the experiment for that one, and then record your result. And then from this feature selection you have done, then you'll be able to see which of the feature is giving me the better result. See, which of these is giving me the better result. Sometimes it might be all the feature that will give you the best result that you need. Sometimes it's possible to have such a thing. But sometimes you might find out that you are getting the best result when you use the best 4. Therefore, if you get the best result here, best result gotten when you use only 4 features, then this is going to be your final identified number of features. You now go now, of course, you can discuss this, try to see, okay, why am I getting better result for lesser number of features? Or why is it not the case? Sometimes you might have techniques 1 getting better result for all, while techniques 2 is getting better result for not all of them. So we try to discuss and see what could be wrong, what could be responsible. Now, so once we are done with the feature selection, which of course is optional. You see, if your result is good from the original data set, you might not need to go there, except if your client is more interested in reducing the number of features. You can tell them, you want me to build, although I'm getting 99% accuracy already, but if I reduce the number of features, it will make it easier for you to get the number of attributes to predict. So it's going to reduce the time, the cost of gathering data. Why not? You can do that for us at the second stage. That will be fine. But sometimes you don't have option, you just have to try feature selection, especially if your result is not achieving what you are envisaged that you want to get. Now, once you are done with that, then you move to discussion of the final result. So from the experimental result above, now you choose the best option from the number of features used. You have identified the number of features, which now is 4 features. Select those 4 features, and the best parameter identified. You already identified best parameter before. Then use it to develop the final model, and then plot the necessary graphs and table like confusion matrix, because this is where you are going to have the final result. So plot the confusion matrix, the area under the curve, if it is classification problem or root mean square error, or you plot predicted versus target if it is a regression problem. So in regression problem, so you want to show me this is the original data given to me. This is the original data given to me, but this is my model. My model is passing through some data, but not all the data. Or after my feature selection, I was able to get a model that passes through all the data points. That means you are getting like almost 99.5% accuracy. So it's possible to have this kind of thing after you have done the necessary optimization and possibly feature selection. So the result of using the best option based on the optimal parameter, you now put the result here now. This is your final result. So after you have selected the features, and if you decide not to do feature selection, that means, okay, that's fine. Then you develop a final model and then validate it and put the result here. I want us to know that you can see that mostly I always mention only one result. Somebody will ask me maybe later, what about training results? Usually we are more interested in testing results, testing accuracy or validation accuracy. We only use the training accuracy when we are just checking, is it overfitting or not overfitting? Because people are not interested in knowing the accuracy of your training sets. Because training set could be accurate, but your testing set is not good. So that is why usually we put out there for people to see the outcome of our testing experimentation after we have trained our model, which is very important. So here you also put the result in the table, and then you discuss the result. What can you see there? And what are the possible implications of what you have seen? So, and how can you possibly interpret what you have in your table? This is why you describe it. So what are the percentage, what is the percentage improvement that you achieve when you carry out feature selection? Does the effort you put into feature selection really worth it? So this is where you kind of try to discuss the result and you move on. In the further discussion section, here you are advised to, if somebody already work on the area you are working, it becomes compulsory for you to put this further discussion. Then you now try to compare. See, I said here you put the result of previous work on the same data set, side by side, your final result. Put them side by side. And then to see how is your work better than their own. Put in your confusion matrix and so many other parameters that will really display the result of what you have achieved. or of your experiment. Compare with the previous work. So discuss the final result and compare with earlier work targets. Use plots or figures and tables to present the result in interesting pattern. You see, I say even if there are no earlier works, you can use more plots and better discussion here. Even if there are no earlier work you want to compare with, this further discussion section, though it's optional, it's an opportunity for you to further discuss your result, tell us the implication, interpret the meaning of what you have achieved, especially maybe in your field, in engineering. What is the implication of this prediction you have achieved? When you are designing a house, how it can prevent possible building collapse, and so many other interpretations that you know in your field that you can actually use to justify the result that came from your experiment. This is under the further discussion. Of course, as in any other research work, you also conclude and recommend. You go into conclusion and recommendation. I say here you conclude your work and provide suggestions for possible future works, where you restate the research problem addressed in your paper. Restate it here in your conclusion. Tell us what is the research problem you have addressed. Summarize your overall arguments or findings. What did you find out? Are you in line with what has been done earlier, or were you able to get something really unique that you want people to pay attention to? So suggest the key takeaway of your results. Tell us the key takeaway that you want people to pay attention to. That is the conclusion. So some people, once they read your paper abstract, the next thing they want to see the conclusion, seeing what actually you achieved before they go into deciding whether they need to buy your paper or they need to read your full paper. Of course, it's always recommended to include possible future works. So this is my own way of doing things, but some people said if you include future work in your paper, people will go and do it before you do it. I say, how many do you want to do? Why don't you benefit people? You see? So my own policy is include as many, because while you are working, see, we call something, as you are working on this thing, we call something fence in and fence out. Fence out. Fencing is as you are working on your research, a lot of ideas will be coming. Don't get distracted too much. You know, hey, I can do this, I can use deep learning, I can use ensemble. Keep documenting those things. So as you are going along the way, fencing are those things that you have to include compulsorily in the present work. The fence out are those things that, though they are related to what you are doing, but you felt that if you include it now, it can really distract the reader. It's not yet time. We call them fence out. So you put them as part of your future work. Recommend to people. Actually, people will like to read your paper if they know that when I read your paper, I'm going to know what are the future likely opportunities in that kind of research. But however, I've seen someone, a research partner once told me, he said, no, why do you need to put a future work? People will do it before we do it. I said, how many future work did you put in your previous work and you are able to finish? Because idea will keep coming. Instead of hoarding those ideas, and some of them will rot in your system, you will never have the time to do it. Personally, I rather prefer to include it. If somebody decides to take it from my paper and do it before I have the time, I mean, at least, well, like you're going to get reward for benefiting somebody. So to me, this is a recommendation that is really very good. And actually, it enhances actually your work. Sometimes it makes the reviewer also to really know that, yeah, you have really done something and you really understand the area, and you can actually identify some of the future research direction that people can follow. Because to me, the essence of getting all this thing done and sending it out to people as published work is to benefit people. And one of the benefits is not just for you to work, you also need to recommend for people reading your paper. These are possible opportunities that whosoever is interested might explore. So, and of course, finally, don't forget acknowledgement to those people. Maybe if it is a sponsored project, acknowledge the appropriate person, acknowledge the appropriate person, people help you along the way. It's not everybody that can be an author. Some people just help you do some little things in the lab. Okay, you can acknowledge them. It's different from being a co-author. Why also, of course, people contribute a lot to be co-author should all be included as appropriate. Of course, references is very important. So put all the references. Whatever citation you have made, you also need to include it in the reference list as much as possible. Anything that is not cited should not be here. In this is the situation. We all know that. So And then, of course, it's good to use reference manager. Don't do manual referencing. Personally recommend Mendeley Reference Manager. It's free. And from my experience with others, it's very light. So you can easily add your paper from online, just search for any paper, click the link, and then you open it, it will extract the reference for you automatically and insert it into your system. So personally, I used to use other method, but I've changed to it for a long time and it's really been doing fine. And then any other thing regarding that is some of the things we want to cover at this phase. So next we move further later. So inshallah to look at some of the sample algorithms, how they work and how we can work with them. And hopefully also we're going to look into sample practical example of a research paper from different fields so that we can hopefully see how it could be applicable to our own area of application. And then hopefully we can take a couple of lessons while we are also writing our own documentation of our experimental setup. So thank you all. So this is what we're going to have for the week. So if there's any question, we're going to take a couple of questions. So barakallahu fikum. So wish you all the best. Thank you very much, everybody. Wa sallallahu ala sayyidina Muhammad wa alihi wa sahbihi ajma'in. Assalamu alaikum.